Hey everyone, and welcome. Today, we're diving deep into something called redox reactions. And trust me, these are the chemical reactions that literally make our world go round. From the energy that powers your body to the juice in your phone's battery, it's all about electrons on the move. So, let's jump right in. So, just take a look at this for a second. On one hand, you've got this brilliant, violent flash of light from magnesium burning, and on the other, you have a simple battery, just quietly doing its thing, powering a device. I mean, they couldn't look more different, right? But believe it or not, they are both powered by the exact same fundamental principle, redox. So the big question is, how? Well, to figure that out, we gotta wind the clock back a bit. See, the first chemists to study this stuff hadn't even discovered electrons yet. So they had to come up with a simpler way to think about it, one based on what they could see and measure, which usually involved two of the most common elements around, oxygen and hydrogen. And what they came up with was actually pretty straightforward. They saw something burn, like magnesium, and said, aha, it's combining with oxygen. Let's call that oxidation. Or if hydrogen was removed, that was also oxidation. And reduction? Well, that was just the complete opposite, taking oxygen away or adding hydrogen. For the reactions they were working with back then, this simple model worked surprisingly well. But there was a catch. As science marched on, chemists started running into all sorts of reactions that looked and felt just like oxidation, but there was no oxygen or hydrogen anywhere in sight. What about when things reacted with, say, chlorine or fluorine? The classical view just fell apart. It was a good start for sure, but it was clear they were missing a huge piece of the puzzle. And that missing piece, that discovery, changed absolutely everything. Scientists finally realized the real story wasn't about swapping entire atoms. No, the secret was much, much smaller. It was all about the electron. In this picture right here perfectly explains the modern idea. You see that sodium atom? It has one lonely electron in its outer shell that it's just dying to get rid of. When it loses that electron, we say it's been oxidized. Now, that electron has to go somewhere, right? And it just so happens that chlorine over there is more than happy to grab it. When the chlorine atom gains that electron, we say it's been reduced. And that simple handoff, that's the heart of every single redox reaction. So how on earth do you keep that straight? Oxidation is loss, reduction is gain. It can get confusing. Well, luckily, chemists came up with this fantastic little mnemonic, oil rig. Just remember oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. It's so simple, and it will save you every single time. Okay, this brings up two other key terms that can feel a little backward at first. The thing that loses electrons, or sodium, is called the reducing agent. Why? Because by giving up its electron, it causes the chlorine to be reduced. And the thing that gains the electrons, the chlorine, is called the oxidizing agent because it causes the sodium to be oxidized. They always work in pairs. You can't have one without the other. But that raises a question, right? Why do some reactions happen and not others? Well, it's basically a competition for electrons. Some metals are just way more generous with their electrons than others. As you can see here, zinc will gladly hand over its electrons to copper ions. Copper will then pass its electrons on to silver. But it doesn't work the other way around. Copper can't force zinc to take electrons. This sets up what we call a reactivity series, with zinc being the most willing to give up its electrons in this group. Okay, so that all makes sense for simple ions where electrons are clearly won or lost. But what about in big, messy molecules where electrons are being shared? How do we follow the action then? For that, chemists came up with a really clever accounting system for electrons. It's called oxidation numbers. So, an oxidation number isn't a real charge. It's more of a what-if number. We look at a molecule, like water, and we see that oxygen is way more electronegative. It's greedier for electrons than hydrogen is. So we just pretend that oxygen completely wins the tug of war and steals the shared electrons. This little bit of make-believe gives oxygen an oxidation number of -2, and each hydrogen gets a +1. It's just a bookkeeping trick, but it's incredibly useful for seeing how electron density shifts around. And the best part is, we don't have to guess these numbers. There's a simple set of rules, kind of like a cheat sheet, that chemists developed to assign them. For example, any pure element, all by itself, always has an oxidation number of 0. The number for a simple ion is just its charge. If you follow these few rules, you can figure out the numbers for pretty much any compound and track where the electrons are moving. All right, so now that we get the whole electron transfer idea and we have our bookkeeping tool with oxidation numbers, we can start to see redox in all sorts of different chemical reactions. So let's take a quick tour of the main types. First up, you have combination and decomposition reactions. Combination is just what it sounds like. Two or more things combine to make one bigger thing, like carbon and oxygen making CO2. That's a classic redox reaction. Decomposition is the opposite. One thing breaks down into smaller parts. But here's the crucial thing. Not all decompositions are redox. If the oxidation numbers of the elements don't change from start to finish, then no electrons actually moved, and it's not a redox reaction. Next up are displacement reactions, and these really show off that competitive electron transfer we were just talking about. You get a more reactive element, like zinc, and it literally kicks a less reactive one, like copper, right out of its compound. It just swoops in and steals its spot. And the same exact thing happens with halogens, where a more reactive one will displace a less reactive one. And then you have this really weird and fascinating special case called disproportionation. Now this is cool. It's where the same element in the same starting substance gets both oxidized and reduced at the same time. A great example is hydrogen peroxide. In that reaction, one of its oxygen atoms gets reduced to make water, while the other gets oxidized to make oxygen gas. Pretty much any element can do this, with one big exception: fluorine. It's the most electronegative element there is. It's the ultimate electron hog, so it only ever gets reduced. It never gives electrons up. So, we have the theory, we know how to track the electrons, we can spot the different reaction types, but so what? Why does any of this matter? Well, this is where it all comes together. Because once you understand how this electron flow works, you can start to control it and harness it to do some pretty incredible things. And this is the Daniell cell, the classic example of how we can put redox to work. What we've done here is actually pretty genius. We've taken a spontaneous reaction and simply separated it into its two halves. Over on the left, the zinc is getting oxidized, releasing its electrons. Over on the right, copper ions are waiting to be reduced, and they need those electrons. By making the electrons travel through that external wire to get from the zinc to the copper, we've created a moving flow of charge. In other words, an electric current. And that's really the whole trick. We are taking the energy stored in chemical bonds and converting it directly into useful electrical energy. Oxidation happens at one end, the anode. Reduction happens at the other end, the cathode. And that simple, elegant process right there, that's the basic engine inside every single battery you have ever used, from the one in your car to the one in your watch. And it's not just about batteries either. This stuff is incredibly practical in the chemistry lab. Chemists can use the really distinct color changes that happen in some redox reactions to perform what's called a titration. It's a way to measure the exact concentration of a chemical in a solution with amazing precision, all because we can predict exactly how those electrons are going to move. When you really stop and think about it, redox is everywhere. It's in the photosynthesis that creates the air we breathe, it's in the metabolism that powers our cells, it's why iron rusts, and it's why your phone turns on. It is the fundamental engine of change. Understanding it is about more than just chemistry. It's about understanding the flow of energy through our entire world. Which leaves us with one big question: where will it get it to take us next?